Hi boys and girls, this is lecture 5.6, the topic, the fundamental theorem of calculus, part 2. In this lecture, we're going to discuss the second fundamental theorem of calculus. If f is continuous on an open interval I containing a, then for every x in the interval, the derivative with respect to x of the integral of a function from a to x is equal to f of x, the function. Notice that the upper endpoint of integration is now a variable in terms of x. Therefore, the integrand is written with a different variable to avoid confusion. But since the upper endpoint of integration is now a function, this means we are integrating to get a function rather than a number. Using the second fundamental theorem of calculus is easier than you think, since you're taking a derivative of an integral. You have inverse processes operating on the integrand. For example, when you square the square root of x, you have inverse operations operating on the argument of the function. In essence, they cancel each other out, giving you the result x. This is going to happen here as well, except we have to consider that the upper endpoint of integration is a variable. So to evaluate this, we'll take the derivative of the integral from 0 to x of this function, the square root of t squared plus 1 dt. The result will be the square root of x squared plus 1, a function rather than a numeric value. What would be the advantage of evaluating a definite integral and obtaining a function rather than a specific value? This example will demonstrate that purpose. We're going to evaluate this integral from 0 to x cosine t dt. Notice it asks us to evaluate it at several x values. Obtaining a function rather than a specific value will allow us to do this. The integral then is sine of t from 0 to x. Now we can use this function to find several values of the definite integral. Let's start with x equals 0. We're being asked to find sine of t from 0 to 0. Of course, that's going to be sine of 0 minus sine of 0, which is 0. We didn't really need to subtract these two values because we know that when the endpoints of integration are the same number, the value of the definite integral is 0. But more importantly, there's no area under the curve. We have moved from 0 to 0 on the x-axis, accumulating no area. Let's try pi over 6. Now we're being asked to evaluate sine of t from 0 to pi over 6. This will be sine of pi over 6 minus sine of 0, which is 1/2 minus 0, which is 1/2. So the value of the definite integral when x is pi over 6 is 1/2. But more importantly, we know now that the area under the curve from 0 to pi over 6 is 1/2. So now we have found the value of this area. Let's try pi over 4. We would be asked to find then the value of sine of t from 0 to pi over 4. This will be sine of pi over 4 minus sine of 0, which is the square root of 2 over 2. That's the value of the definite integral when x is pi over 4. But more importantly, now we have found the value of the area under the curve from 0 to pi over 4. So notice we've added more area as we have changed the endpoint of integration. I'll try to make it sort of a different orientation so you can see. That now is the value of the definite integral from 0 to pi over 4, and that is the area under the curve. Let's try pi over 3. Sine of t from 0 to pi over 3, of course, is sine of pi over 3 minus sine of 0. This is the square root of 3 over 2. The value of this definite integral when x is pi over 3, but now we've accumulated more area under the curve as we've changed the endpoint of integration. Now from 0 to pi over 3, we have more area under the curve. I'll try it this way. And then finally, let's evaluate the integral when x is pi over 2. Sine of t from 0 to pi over 2 is equal to sine of pi over 2 minus sine of 0. Sine of pi over 2 is 1, minus 0 of course is 1, and now we have the value of the definite integral from 0 to pi over 2, and that is an additional area accumulated under the curve. So notice now we can think of the function capital F, the antiderivative, as accumulating the area under the curve f of x equals cosine x from t equals 0 to t equals x, whatever x value we choose. When x was pi over 6, we had accumulated this area. When x was pi over 4, we had added a bit more and accumulated all of this area. When x was pi over 3, we added this bit and it was all of this area, etc. So that is the value of allowing your upper endpoint of integration to be a function so that you can look at area at several endpoints of integration rather than just one. The last topic we're going to discuss in today's lecture is particle motion, and we're going to look at the difference between displacement and total distance traveled. If we examine the velocity of a particle moving along a straight line where s of t is the position at time t, then its velocity is v of t, which is equal to s prime of t, the first derivative of position. And the integral of velocity is position. Furthermore, the integral at certain endpoints of integration from a to b will be the position at b minus the position at a. This definite integral represents the net change in position or displacement of the particle. However, if we want to calculate the total distance traveled by the particle, we must consider the intervals where v of t is less than or equal to 0, and the intervals where v of t is greater than or equal to 0. When the velocity is negative, the particle moves to the left, and when the velocity is positive, the particle moves to the right. To calculate the total distance traveled, we must integrate the absolute value of the velocity function in order to get that total distance. Let's demonstrate this with a simple example. Let's suppose that you want to travel 20 feet. And you move along until you reach the 10-foot mark and realize that you have dropped something along the way. And you reverse your position and start moving backwards. You travel backwards 5 feet and find the thing that you dropped. And once you pick it up, you continue on your way until you reach the destination, which was 20 feet all along. Now that means that from the 5-foot mark, you had to travel another 15 feet. If we're just talking about displacement, which is a net change in position, all we would really be interested in is you started at 0, you ended at 20. Your net change in position is 20. But if we wanted to talk about total distance traveled, we would need to take into account the initial 10 feet that you walked, and then the 5 that you walked backwards, and then the 15 that you walked, the remaining 15 that you walked to get to your destination. That would be 10 plus 5 plus 15, which is 30. So here we have a graph which represents velocity of a particle. Where the velocity values are positive, the particle is moving to the right. Where the velocity values are negative, the particle is moving to the left. And then here we have a section where the particle is moving to the right again. But when integrating, remember we get area under the curve. And when integrating this positive section, we would end up with a positive region here. Integrating this negative section will give us a negative region. And of course, once again, integrating this positive section would give us a positive region. To get displacement, we would take the positive, add the negative, and the positive, and that would give us simply a net change in position. But to get total distance, we need to take into account the time when we were moving to the left. So we would need this positive region, we would need the absolute value of this negative region, and then we would also need to add this positive region. Therefore, to get displacement on the interval AB, we're going to integrate from A to B the velocity function as is. That will give us A1, this section, minus A2 since it's negative, and then plus A3, net displacement. But to get total distance traveled on the same interval, we'll integrate from A to B the absolute value of the velocity function. What this will do is, of course, A1 will be positive, but it will make A2 positive as well. And then when added to A3, it will give us total distance traveled. In our last example, we're going to find displacement and total distance traveled by a particle. Its velocity function, t cubed minus 10t squared plus 29t minus 20. Here is a graph of that function. You can see that from 1 to 4 in the interval, the velocity values are positive, which means the particle is moving to the right. But from 4 to 5 in that interval, the velocity values are negative, which means the particle is moving to the left. When we integrate this function, it's going to give us this positive region and this negative region. For net displacement, we add the positive and the negative to get the net change in position. But for total distance traveled, we'll need this positive region, and we'll need to make this negative region positive by taking the absolute value of the velocity function. That way, the positive and positive will give us total distance traveled. Let's start with displacement. We're going to integrate the velocity function from 1 to 5, and that will be t cubed minus 10t squared plus 29t minus 20 dt. The antiderivative, 1/4 t to the 4th minus 10 thirds t cubed plus 29 halves t squared minus 20t, of course evaluating from 1 to 5. After multiple calculations performed faster than the eye can see and with invisible ink, we arrive at the value of this definite integral, which is 32/3. This is displacement. The particle started somewhere, ended up somewhere, and that net change in position was 32/3 without taking into account any reversals. Now let's find total distance traveled. This means we'll need to integrate the absolute value of the velocity function. In doing so, we'll need to split the integral into two integrals. We'll need to integrate from 1 to 4, the velocity function, and then we'll need a separate integral from 4 to 5. And the integral from 4 to 5 will produce a negative value, so we're going to need to make that value positive. That means we'll integrate from 1 to 4, t cubed minus 10t squared plus 29t minus 20 dt. And then since we know that this value will be negative, instead of adding it, let's subtract it. And that will in effect make it a positive value from 4 to 5 of t cubed minus 10t squared plus 29t minus 20 dt. Of course, that means we're going to have 1/4 t to the 4th minus 10 thirds t cubed plus 29 halves t squared minus 20t from 1 to 4, and then minus 1/4 t to the 4th minus 10 thirds t cubed plus 29 halves t squared minus 20t from 4 to 5. Remember, we're subtracting the value of this integral. Once again, multiple calculations are occurring at light speed, and we end up with 45/4 minus the negative value of this integral, which was -7/12. When we add 45/4 and 7/12, we get 71/6. This was the total distance traveled versus net displacement. That's it for today's lecture. I leave you with one last integral. God bless you, boys and girls.